Welcome to Introductory Chemistry. In this chapter, we will be exploring the importance of chemistry. We'll address the question, what is chemistry? And we'll discuss the scientific method and how it is used to solve problems. We'll also touch upon some of the strategies for learning chemistry. Chemistry is extremely important in everyday life. Everywhere you look, you'll find chemistry plays an important role. We rely on chemistry to develop the materials we use in everything from cell phones to automobiles. Chemistry is central to the development of medicines and other healthcare products. In fact, modern-day living would not be possible without chemistry. Furthermore, knowing some chemistry and understanding how scientists think can help you make better decisions about the questions and problems that confront us all every day. In this course, we'll learn about the basic principles of chemistry. This includes the properties of matter, the nature of the elements and atoms, how chemical reactions occur, and much, much more. We'll also learn about the importance of observation and analysis and develop an ability to view the world from a new perspective. Most importantly, through chemistry and with a good deal of practice, you will become a better problem solver. So what is chemistry? Chemistry is the study of matter and the changes that substances undergo. It's often called the central science because it is so extensively connected to other fields. For instance, geologists use chemical techniques to identify rock samples. Oceanographers use chemistry to track ocean currents, nutrients, and the effects of global climate change. Physicists and astronomers use chemistry to explore the properties of substances on subatomic and cosmic levels. Biologists use chemistry to understand the processes that sustain life. In fact, it is difficult to name a scientific or technical field that doesn't utilize chemistry to some extent to answer questions and solve problems. So how do chemists answer questions and solve problems? The first step is recognizing and formulating the problem or question clearly. This generally involves making pertinent observations. The observations may be qualitative, as in the sky is blue, water is liquid, and so forth. Qualitative observations describe properties or occurrences in ways that do not rely on numbers. Alternatively, the observations may be quantitative. Water boils at 100 degrees Celsius, or the density of gold is 19.30 grams per cubic centimeter, and so forth. Quantitative observations involve measurements, which by definition consists of both a number and a unit. In either case, after choosing to learn more about an observation or set of observations, the next step is to generate a hypothesis, which is a tentative explanation for the observations. The hypothesis may not be correct, but it puts the observations into a form that can be tested. For example, a hypothesis can be formulated to explain the observation that dinosaurs disappeared from the Earth. The hypothesis might be that the impact of an extraterrestrial object caused their extinction. We can now test the hypothesis. Like many hypotheses, direct testing is not possible, but additional data may be collected to support or refute the hypothesis. So once a hypothesis is formed, scientists conduct experiments to test its validity. Experiments involve systematic observations and measurements that may be made ideally under controlled conditions that challenge and explore the original hypothesis. Experiments generally produce new observations and data that allow for extensions or modifications of the original hypothesis. As the hypothesis is modified, even more experiments may be devised to further test whether the solution or explanation reasonably explains the observations. These basic steps for problem solving are fundamental to the scientific method, which seeks to explain and understand the world around us. This understanding is not static, but is instead a dynamic framework where knowledge is continuously collected and organized. Science, then, can be viewed as the plan whereby information is collected, processed, and analyzed. The plan will vary depending on the nature of the problem. The exploration of those questions and problems is continuous and ongoing as current beliefs and expectations are challenged by new observations, experiments, and insights. This process of problem solving is at the heart of the scientific method, which is a body of techniques for investigating phenomena, acquiring new knowledge, or correcting and integrating previous knowledge. The process of the scientific method begins with the basic problem-solving methods of observation, hypothesis, and experimentation. As more experimental data is collected and analyzed, the results may be considered sufficiently reproducible or dependable. These results may then be summarized into a law or a theory. The chief characteristic which distinguishes the scientific method from other methods of acquiring knowledge is that scientists seek to let reality speak for itself. This means supporting a theory when a theory's predictions are confirmed and challenging a theory when its predictions prove false through experimentation. Suppose you were involved in the following scenario. Your instructor is holding a balloon and quickly inhales some of the gas inside the balloon. He then speaks and his voice changes to a high-pitched sound. He asks you to determine what gas was inside the balloon. Based on your observations, you conclude that the gas must be helium. Your first step is to make observations. You might state that the problem or phenomena was a changing vocal pitch. You might also have noticed that the instructor did not seem to suffer any long-term effects that would have occurred if the gas had been poisonous. That's another observation. You may have formulated a hypothesis based on previous experience with helium balloons. To confirm your hypothesis, you would need to conduct further experiments. For instance, you might subject the gas in the balloon to a flame test to rule out flammable gases. More definitive experiments could follow to further characterize the nature of the gas and its effect on the vocal cords or humans. As you can see, a single observation can generate numerous follow-on experiments, resulting in still more observations. From the previous diagram on the scientific method, we can see that explanations for observable phenomena can take several forms. The first, a law, is a verbal or mathematical description of a phenomena that allows for general predictions. A law simply says what happens. It does not address the question of why. Laws are unlikely to change greatly over time. And once again, a hypothesis is a proposed explanation for a phenomena. For a hypothesis to be a scientific hypothesis, the scientific method requires that one can test it. Initially, scientists might utilize a working hypothesis that will be further refined or modified. A theory seeks to explain why a particular phenomenon happens. Theories are also subject to refinement and modification. Nevertheless, theories are well-substantiated explanations that are repeatedly confirmed through observation and experimentation. High-quality theories aim for significant predictive power and explanatory force. Scientists use theories as a foundation to gain further scientific knowledge. They also use theories to accomplish goals such as inventing technology or solving significant problems such as curing disease or addressing global climate change. Ultimately, learning chemistry is a major endeavor. It has its own vocabulary, which you must learn and understand. There are many new concepts and principles to be memorized. Most importantly, the study of chemistry involves solving a large number of different kinds of problems. It's important to practice your problem-solving skills so that you can easily recognize familiar problems and quickly figure out new ones. You'll need to make sure that you understand where you have made mistakes so that you can correct them the next time. Chemistry is a rich and deep science that's developed over time because of the human drive for answers to the very big questions that we encounter. So it's only fitting that if there's something that you don't understand about chemistry, you should ask questions too.